Hey, today I am experimenting with a homemade discrete voltage regulator using a negative feedback principle that is employing an op-amp and a series pass transistor to regulate the output of the voltage into the load. So if we quickly take a look at the actual brief description of the circuit itself, here is my input voltage. This is unregulated input voltage. It could I've designed it so it operates between 20 to 25 volts input. So typically you can get like a 24 volt transformer or anything after a rectifier could be basically put in here. Here I have my input filter. It's a 1000 microfarad, 50 volts. And this is the actual regulator. This is the actual discrete regulator. I use nominal 6.9 volts Zener as my reference, and that's fed into the positive input of the op-amp, and the op-amp is a TL082. It's a very high slew rate, high bandwidth op-amp, so it's able to respond very quickly to any changes in load here. So that's why I chose TL82, because it's a very fast op-amp, relatively fast op-amp. I have here a current limiting resistor that biases the Zener reference. I have here a 5 ohm series resistor just here to protect the transistor if it was to be shorted here at the output, so that you don't get all the current passing through the series transistor, thereby destroying it. So basically that's there for protection. And I use a feedback of 3.2K and 6.8K into the negative input of the op-amp, and I trim it using 100K resistor in parallel with a 6.8K. My output voltage is 12 volts. So I'm trying to regulate to 12 volts. So your typical output that could be used for a lot of different things. For now, I have designed it such that it could be used between 0 to 120 milliamps of current. That's the load, but this can be increased by just adjusting just adjusting this resistor. You can make it a higher wattage resistor, and you should be able to quickly adjust it. It can go as high as 1 amp, but I just don't want to do that right now. So that's basically it. This is very classic. This is actually used inside a lot of IC regulators, like the 7812 regulator, for example. The 7812 regulator, they use typical arrangement inside the IC to accomplish the same thing. Yeah. And by the way, this can also be made a variable. It could be made a variable. You can get a variable output here by just playing around with this feedback resistors. And making them, if you make them, for example, this, I can trim the voltage between 10.5 volts all the way to 12.5 volts, right? So by just playing around with this trim pot here, I'm able to do that. Alright, so to the demonstration of this circuit. It is sort of a mess, but I hope you bear with me here. I'll start with the input voltage. Okay, so this is my power supply, and this is the input into the regulator. I have a 20 volt input at the moment, and this monitors my output current. Basically, we'll see how much load I have. Right now it's barely loaded, so it's just measuring 115 microamps or 120 microamps, thereabouts. Here, this meter here is measuring the Zener reference voltage. This is measuring the current going into the Zener reference. So basically it's measuring this current here, this current that goes into the zener. Okay, that will be this meter. So right now it's about 11.2 milliamps. This measures the output voltage, the regulated output voltage, which is around 12 ohms, 12 volts. This one is not measuring anything. I was just using it to troubleshoot part of this circuit. And here my scope, one of my scopes, is measuring the channel 1 input is measuring the output of the op-amp, which is the corrective signal, into the series pass transistor. So it's measuring this node here. So this is the corrective voltage necessary to keep the output constant. And well, this is also called the negative feedback, which is called the error voltage that's fed into the op-amp. And I'll show you which another scope that's measuring that. But going back to this scope here, channel 2 is measuring, if you see, channel 2 is right here. Channel 2 is right here, and it's measuring the that's the load voltage. It's measuring the load voltage. So that's measuring the load voltage, and you can see it's about 12 volts. It's about 12 volts. So, and you can see that's the corrective output from the op-amp, the corrective signal output, and it's around 12.8. Okay, going back to my Agilent or HP scope here. The channel 1 is measuring the positive input of the op-amp, and channel 2 is measuring the negative input of the op-amp, so which is the error signal. And basically, if you see here, they're both basically the same. You can see channel 1 is around 7 volts and channel 2 is about 7 volts or thereabouts. Okay, and I also have an output filter here. It's not necessary, but at higher loads, I found that there was quite a bit of high oscillations around 2 megahertz. So I just hang this. You can put anything. I just grabbed one 1000 microfarad capacitor just to take away all the high frequency noise that was going, because the op-amp was trying to correct when it's at a high load, which is around 120 milliamps. It was going like crazy trying to correct for the because this voltage is trying to dip, this one is trying to keep it up, and it goes up and then corrects it to brings it back down. So there was quite a bit of oscillations here, and so when I put this, everything went away. And also there was oscillations at the reference here. And also that was, I put the 100 nanofarad capacitor here just to take away all that high frequency oscillations that was happening at the reference as well. Okay, so to the demonstration. So what I'll do is I will vary the load using this pot here. This pot is the 100k resistor that we have here, and this has this limits the how much maximum current comes out when this pot is all the way at the top here, which means it's the low, when it's the lowest resistance, it will limit it to around 115 milliamps. So I'll vary the load using this resistor here, this pot. This resistor is used to trim my output voltage, which is basically, it's that 100k resistor here. So if we bring back here, this is the 100k resistor that's used to trim the output, so which means the feedback that goes into the or the error signal that goes into the TL82 op-amp. So I can use that to trim it. So if you can see here, so if I could put both of them at the same shot, hopefully it will focus. Okay, so if you see, so just monitor that output voltage here while I vary this. So if I vary it, you can see that, yeah, I can trim the output voltage. So let's trim it to 12 volts. There. Okay, and we'll just leave it at that. And like I said, this is the zener voltage, the reference voltage. This is the Yeah, that's the current that's going into the zener, which is the IZT. So if you were to, if we know that from zeners, that there is a current that needs to go through the zener to make the zener regulate at that voltage. So this is about 10 milliamps, so I have around 11.2 milliamps going into the zener. Okay, so let's vary the load and let's take a look. Let's take a look what happens to the so the best way to keep your eye on the output voltage. And also, I will show you here. This keeps turning off. Okay, so let's see if I can get both of them on this same shot. Oh, that wouldn't be very, very visible. So I'll just increase the current using this guy, and then this guy here. I'll increase the current. You'll see. Well, we're just gonna go all the way to full load. I don't care. So if we go to full load, so you can see it's increasing. There you go. That's my full load. It's 115 milliamps or 116 milliamps going, and take a look. The voltage remains constant. The voltage remains constant. That's the output, and that's, there you go. That's the current going through the whole the load current, and you can see that the corrective signal is at 12.9, and the output voltage is around 12.3. That's not quite accurate, so we'll go back to here. So that's 12 volts, and you can see the op-amp positive and negative input are still the same, and they're still 7 volts each, the positive and negative input into the op-amp. And you can see my zener reference remains the same, and let's take a look. The current going into the zener, same thing, remains the same. Let's put it to high res mode. There you go. Oh, sorry, I took it out. Well, okay, sorry. It doesn't go high res mode at that amount of current. Yeah, there you go. And the voltage remains constant. So this regulator is working correctly. And you can see that there's actually one of my load resistors getting hot. This is like a 1 watt resistor. Anyway, so we'll dial down the so see if I can put both of them on the same shot. Yeah, so if I was to dial down, so let me see. Okay, so that is the load current. This is the load voltage that's regulated. So keep your eye as I lower the voltage, as I lower the load current. You can see the voltage remain. You can see that voltage remaining constant. So yeah, so from full load to no load, the voltage remains constant, and this is accomplished, like I said, with a negative feedback on the op-amp. So we know from op-amp theory that the op-amp will do whatever it can at its output when it has negative feedback. That's only applies when it's in negative feedback mode. It will do anything it can on its output to make these two inputs the same. So by using that principle, the reference is constant, right, since we have it biased correctly, and on the negative we're getting a sample voltage, so it will change its output, thereby driving the transistor correctly, giving it the correct voltage to maintain that constant voltage in the output, and it will monitor it continuously through this negative feedback, and it doesn't matter when the load increases or decreases, it will monitor it continuously and thereby maintaining the output voltage here. Okay, another thing I'll demonstrate is also by increasing my input voltage. We demonstrated it by increasing our load, but now we will demonstrate it using by if we increase our input voltage. So take a look at your output voltage here, and I will increase the input voltage. So I'll just put them both in the same shot. If I were to increase the input voltage, you can see there you go. So it stayed relatively constant from 20 to 25. So a change of 5 volts produced only a change of few millivolts, basically a few millivolts of change. And the reason that changed it is because the Zener, the Zener reference went from 9.7, 6.97 volts to 7 volts, right? So that change, it also affected that. But you can get a stable Zener here, and actually you can fix that by introducing, instead of a resistor here to actually bias the Zener, you can fix that by introducing a current source. If this was a current source, and a current source we know has a constant current output, so if you were to replace this whole resistor with a current source, then it doesn't matter even if the right now it's performing okay, but if you were to run and maintain absolute constant voltage on the output, then you can change it, you can replace this with a current source, and that current source will bias the Zener reference with the correct current, and it doesn't matter what the input voltage is doing, then that current will remain constant, thereby maintaining the positive input of the op-amp constant reference, and which by there, when it applies correct output voltage in its output pin here, it will maintain the correct voltage. So that can be solved, right? This can be solved, that fluctuation we had from 20. So if I do that again, from 20, if you keep your eye on the output voltage from 20, you can see that it changed, right, by like 30 millivolts or so. So that can be fixed by introducing a current source. And my next video will show me designing, calculating the right values for the current source. So we'll introduce this with a current source, we'll replace this with a current source, and fix that change here, basically. Alright, so I hope this was helpful, and just a little experiment here showing how a discrete voltage regulator can be built. It's very simple, and I have it here on a breadboard, but you can whip it up and make this could be put into PCB, and you can just put it. By the way, my series pass transistor, I'm using an old school power transistor here. It's 2N3766, so that's what I'm using for my my series pass transistor. It's one of those big metal case. You can see the collector is hooked up to there, to the 5 ohms, into the output, the input voltage, to the unregulated input voltage here. Yeah. So that's basically it. This is a look into how to design a discrete voltage regulator. Alright, if you like this video, just give it a thumbs up, or subscribe, all that good stuff. Yeah, thank you very much. See you next time.